The copper wire anomaly. In the spring of 1997, a tobacco farmer in rural Kentucky made a discovery that would haunt agricultural scientists for decades. He wasn't conducting an experiment. He wasn't following any manual. He was simply trying to keep deer away from his seedlings by wrapping copper wire around wooden stakes at the edge of his field. What happened next defied everything he knew about farming. The plants closest to those copper stakes grew faster, stronger, and produced yields he'd never seen before. Not by 10 or 15%, by almost 3 times, he told his neighbors. Most laughed, some tried it themselves, and those who did saw the same thing. This wasn't an isolated incident. Across continents, in different soils with different crops, farmers were noticing something the textbooks never mentioned. A piece of copper wire, buried near roots or wrapped around stakes, seemed to be changing everything about how plants grew. And yet, if you search agricultural journals or university research databases today, you'll find almost nothing about it. This is the story of a practice that works in the field but doesn't exist on paper. A phenomenon observed by thousands but studied by almost no one. And the uncomfortable questions it raises about what gets researched in modern agriculture and what gets ignored. The first documented reports came from home gardeners in the 1980s. Nothing formal, just observations shared in newsletters and community exchanges. A retired machinist in Oregon mentioned that tomato plants near his copper plumbing scraps grew noticeably larger. A greenhouse operator in Vermont noticed the same thing with peppers planted in beds where she'd buried old copper electrical wire to mark boundaries. By the 1990s, enough people had noticed the pattern that small experiments started appearing. A community garden in upstate New York divided plots in half. One side received copper wire buried 6 inches deep around the perimeter. The other side received nothing. Same soil, same water, same seeds. The copper side produced vegetables averaging 8 times the weight of the control side. The organizers expected skepticism. What they didn't expect was silence. They sent their results to agricultural extensions, university departments, and farming publications. Most never responded. Those who did suggested the results were coincidental or that some other variable must have been responsible. But the gardeners knew their plots. They'd been working the same soil for years. Nothing had changed except the copper. In 2003, an agricultural researcher in New Zealand named Dr. Patricia Howarth became curious. She'd heard enough stories from farmers in her region, all describing the same phenomenon with copper wire around fence posts or buried near root zones. The consistency was hard to dismiss. She designed a controlled study using wheat, 3 test groups. One with copper wire placed in the soil, one with aluminum wire as a control for any physical soil disruption, and one with no wire at all. She measured everything: germination rates, stalk thickness, root development, grain yield. The copper group outperformed both controls significantly. Yield increased by 240%. Root mass was heavier. Disease resistance appeared stronger. She published her findings in a regional agricultural bulletin. The response was not what she anticipated. 2 major agricultural journals rejected the paper without peer review. One editor wrote back, saying the results seemed too significant to be attributed to such a simple intervention, and suggested she'd made an error in her methodology. Another simply said the topic wasn't of interest to their readership. Dr. Howarth tried to replicate the study with funding from a university grant. The grant was denied. The committee notes mentioned that micronutrient supplementation was already well understood, and that copper's role as a trace element didn't warrant further investigation. But that wasn't what she was studying. She wasn't adding copper sulfate fertilizer, a known micronutrient source. She was placing metallic copper in soil and observing something that existing nutritional models couldn't explain. The most compelling aspect of these reports isn't just that they show increased growth. It's that they show it consistently across wildly different conditions. Sandy soil in Arizona, clay soil in Ohio, tropical conditions in Puerto Rico, greenhouses in Iceland, outdoor farms in Scotland, different crops, tomatoes, wheat, corn, peppers, beans, squash. The mechanism shouldn't work the same way everywhere, and yet it does. One hypothesis emerged from soil microbiologists. Copper ions, they suggested, might be creating electrical potential differences in the soil, affecting how microorganisms function. Bacteria and fungi in healthy soil communicate partly through electrical signals. If metallic copper was somehow enhancing or stabilizing these signals, it could explain why root systems seem more robust and nutrient uptake more efficient. But this was speculation. No one funded the research to test it properly. Another theory came from electroculture research, a fringe field dating back to the 18th century. Early experiments showed that electrical currents could stimulate plant growth. Some researchers wondered if copper wire was creating microcurrents naturally through contact with soil moisture and minerals. The charges would be tiny, unmeasurable with standard equipment, but potentially significant at a cellular level. Again, speculation, no institutional support to investigate. A third possibility involved copper's known antimicrobial properties. Perhaps the presence of copper was suppressing harmful soil pathogens just enough to give beneficial organisms an advantage, creating a healthier root environment. This seemed more plausible, but studies on copper's antimicrobial effects in soil focused on contamination levels, not low-level presence that might be beneficial. Each theory had merit. None received serious research funding. By 2010, the practice had spread through informal networks, online forums, farmers' markets, word of mouth. People were trying it because it was cheap, simple, and consistently reported as effective. A single strand of copper wire cost almost nothing and could be reused season after season. Agricultural supply companies weren't interested. There was no product to sell beyond the wire itself, no proprietary formula, no patent potential, no profit margin worth pursuing. This is where the story becomes less about science and more about economics. Modern agriculture operates on a model of continuous input. Fertilizers need to be purchased every season. Seeds are often patented and can't be saved. Pesticides, herbicides, fungicides all represent recurring revenue streams. The industry is structured around products that farmers must buy repeatedly. A piece of copper wire doesn't fit that model. Once purchased, it lasts indefinitely. There's no subscription, no repeat sales, no way to build a business model around it. When a solution is too simple and too cheap, it becomes invisible to an industry built on complexity and dependency. In 2015, a cooperative of organic farmers in Vermont decided to conduct their own large-scale test. 43 farms participated, each selected 2 identical plots for comparison. Half received buried copper wire in a grid pattern 6 inches deep, spaced every 3 feet. The other half received nothing. They grew potatoes, a crop where yield differences are easy to measure and economically significant. The results were documented with photographs, weight measurements, and soil tests before and after. The copper plots produced an average of 2.9 times more potatoes per square foot. Not just heavier plants, more actual tubers, larger tubers, better storage quality after harvest. They compiled everything into a report and sent it to the USDA, land-grant universities, and major agricultural organizations. The reception was polite but dismissive. One response thanked them for their interesting observations, but noted that anecdotal results from non-controlled environments weren't sufficient for scientific conclusions. The fact that 43 independent farms across different soil types and microclimates all showed the same pattern apparently didn't qualify as significant data. No follow-up studies were commissioned. No research grants were offered. The report was filed away. Here's what makes this frustrating. Copper is already recognized as an essential micronutrient for plants. It's involved in photosynthesis, enzyme function, and protein synthesis. This isn't controversial. Every agronomy textbook mentions it, but the amounts discussed are trace levels, parts per million, delivered through fertilizers or naturally present in soil. What these farmers and gardeners were observing seemed to involve something different, a physical presence of metallic copper affecting plant growth in ways that dissolved copper salts didn't replicate. Several independent labs tried to test this. They added copper sulfate to soil at various concentrations. Growth improved slightly at optimal micronutrient levels, but it never approached the 200 to 300% increases reported with copper wire. The physical form seemed to matter. But why? That question remained unanswered because no one with resources and institutional backing asked it seriously. There's a pattern in agricultural history. Simple, non-proprietary solutions tend to be ignored until they're independently rediscovered multiple times, or until economic conditions make them suddenly relevant. Crop rotation was practiced for centuries before soil science explained why it worked. Companion planting was dismissed as superstition until research on root exudates and pest confusion validated it. Cover cropping was considered wasteful until erosion costs made it economically necessary. The copper wire phenomenon might be following the same trajectory. It works empirically, farmers see results, but it lacks the institutional validation that would make it official knowledge. And there's little incentive to provide that validation. Universities increasingly rely on private funding from agricultural corporations. Those corporations have no interest in promoting techniques that reduce dependence on their products. Research priorities follow funding. Funding follows profit potential. If something can't be patented, packaged, or sold at scale, it struggles to attract serious scientific attention, no matter how well it works in practice. Some researchers have tried to bridge this gap. In 2018, a soil scientist in Australia named Dr. James Renwick obtained modest funding to study electrical properties of soil with embedded copper. His preliminary findings suggested that copper wire was indeed creating measurable electrical gradients, though far smaller than conventional electroculture experiments. More intriguingly, he found that microbial activity near copper wire showed different patterns than in surrounding soil. Certain beneficial bacteria appeared more active. Fungal networks seemed more extensive. The effect was subtle but consistent. He applied for additional funding to continue the work. The grant was denied. The review committee noted that while the findings were interesting, they didn't represent a significant enough departure from existing knowledge to warrant further investment. This is the paradox. The effects are too large to be easily explained by existing theories, yet not novel enough in their explanation to attract research funding. The phenomenon falls into a gap between what's known and what's considered worth investigating. Today, if you visit online communities focused on sustainable agriculture, permaculture, or homesteading, you'll find copper wire mentioned regularly. People share their results, they post comparison photos, they describe their techniques, wire gauge, burial depth, spacing, crop types. The knowledge exists and spreads, but it circulates outside official channels. It's not in university curricula. It's not in agricultural extension publications. It's not in the farming manuals distributed by major seed and chemical companies. It exists in a parallel network of practical knowledge, passed person to person, tested in actual fields and gardens, validated by results rather than credentials. This isn't how science is supposed to work, but it's how farming actually works when formal institutions don't address what farmers observe. So why does this matter? Because if a simple piece of copper can substantially increase crop yields with no negative effects, no recurring costs, and no environmental downside, then we need to understand why. Not for profit, not for patents, but because global food security depends on growing more food with fewer resources, and we can't afford to ignore solutions simply because they don't fit comfortable business models. The copper wire phenomenon raises uncomfortable questions about what gets studied and what gets ignored in modern agriculture, about whether research priorities serve farmers or corporations, about whether we're missing simple solutions because they're too simple to be profitable. There's no conspiracy here, no malicious suppression, just structural incentives that make certain kinds of knowledge invisible, even when that knowledge works in the field, season after season, farm after farm. The farmers who use copper wire aren't waiting for official approval. They've seen the results. They know what works in their soil. They're moving forward with or without institutional validation. But for the rest of us, for food systems that desperately need more efficient, sustainable methods, the silence around this practice represents a failure of curiosity, a failure to investigate what farmers are telling us, a failure to ask the simple, essential question: if it works, why aren't we studying it? The piece of copper is still there, buried in soil across thousands of farms and gardens worldwide, still producing results that don't make sense according to standard models, still ignored by the institutions that claim to serve farmers and advance agricultural science. And every season, the yields keep coming, 3 times higher, sometimes more. The evidence grows, the silence continues. And somewhere, another farmer wraps copper wire around stakes, not because a university told them to, but because their neighbor showed them the results, because it costs almost nothing to try, because when you work the land, you learn to trust what works more than what you're told should work. That knowledge will keep spreading, quietly, unofficially, one garden, one field, one harvest at a time. The question isn't whether it works. Thousands of farmers have already answered that. The question is, when will the institutions finally pay attention? If this story made you think differently about what gets researched and what gets ignored in agriculture, subscribe to this channel. We investigate the practices and knowledge that fall through the cracks of official science, the techniques that work in the real world but don't exist on paper. Because sometimes the most powerful solutions are the ones no one profits from talking about.